Tonight, we're going to talk about something that should be settled science but isn't: the expansion of the universe. For nearly a century, we've known the cosmos is getting bigger, space itself stretching and carrying galaxies apart. We've measured this expansion rate with increasingly sophisticated tools and techniques, refining our understanding decade after decade. But here's what nobody tells you. Two of our best measurement methods, using completely different approaches and representing the pinnacle of observational astronomy, are giving us different answers. And they're not slightly different. They disagree by enough that one of them has to be fundamentally wrong, or our entire model of cosmology is missing something critical. By the end of tonight, you're going to understand why this disagreement terrifies cosmologists, what it might mean for everything we thought we knew about the universe, and why solving this mystery could revolutionize physics itself. Before we get started, if you love exploring the depths of space as much as we do, take a second to like the video or subscribe. It's a simple action, but it helps this channel reach more curious minds like yours. Now, let's begin. The story starts in the 1920s with a discovery that changed everything. Before Edwin Hubble made his observations, most astronomers believed the universe was static, eternal, and unchanging. Even Albert Einstein thought this. In 1917, when Einstein applied his new general relativity equations to cosmology, he found something disturbing. The equations predicted that the universe should be either expanding or contracting. It couldn't just sit still. Einstein didn't like this result. It contradicted the prevailing wisdom that the cosmos was eternal and unchanging. So he added something to his equations, a cosmological constant, essentially a fudge factor that would keep the universe static. He later called this his greatest blunder, because the universe isn't static, it's expanding. Edwin Hubble proved this in 1929, using observations from the Mount Wilson Observatory in California. Hubble studied galaxies, measuring their distances and their velocities. The distances came from observations of Cepheid variable stars, pulsating stars whose brightness varies in a predictable pattern. Henrietta Leavitt had discovered in the early 1900s that the period of a Cepheid's pulsation was directly related to its true luminosity. A Cepheid that pulsates slowly is intrinsically brighter than one that pulsates quickly. This was revolutionary. If you can measure how long a Cepheid takes to pulse, you know how bright it really is. Compare that true brightness to how bright it appears from Earth, and you can calculate its distance. It's simple geometry. If you know a light bulb's true wattage and you measure how bright it looks from where you're standing, you can figure out how far away it is. The same principle works for Cepheid stars. Hubble used this technique to measure distances to galaxies, proving that many fuzzy nebulae visible in telescopes weren't clouds of gas within the Milky Way, but separate galaxies millions of light years away. The universe was suddenly much bigger than anyone had imagined. But Hubble noticed something else. When he measured the velocities of these galaxies using spectroscopy, analyzing how their light was shifted toward the red end of the spectrum, he found a pattern. Every galaxy was moving away from us. And the farther away a galaxy was, the faster it was receding. Double the distance, and the recession velocity doubled. This was expansion. Not galaxies moving through space, but space itself stretching, carrying the galaxies along with it. Imagine a balloon with dots drawn on its surface, representing galaxies. As you inflate the balloon, every dot moves away from every other dot. From any dot's perspective, all the other dots are receding, and the farther away a dot is, the faster it seems to be moving. That's what's happening with the universe. Space is stretching everywhere simultaneously. Hubble quantified this relationship with what's now called Hubble's law. The recession velocity of a galaxy is proportional to its distance. The constant of proportionality is called the Hubble constant, usually written as capital H subscript 0. This number tells you how fast the universe is expanding. Specifically, it tells you how much faster a galaxy is receding for every additional unit of distance. Hubble's original estimate was around 500 kilometers per second per megaparsec. A megaparsec is about 3.26 million light-years, a standard unit for measuring cosmic distances. So Hubble was saying that for every 3.26 million light-years of distance, a galaxy's recession velocity increases by 500 kilometers per second. That seems fast. A galaxy 326 million light-years away would be receding at 50,000 kilometers per second, about 17% of the speed of light. But Hubble's measurement was wrong. Badly wrong. We now know the Hubble constant is much smaller, somewhere between 67 and 74 kilometers per second per megaparsec, depending on how you measure it. That's 7 to 8 times smaller than Hubble's original estimate. Why was he so far off? The main problem was his distance measurements. The Cepheid variable stars he was using to measure distances came in two types, and he didn't know this at the time. Classical Cepheids and Type II Cepheids follow different period luminosity relationships. Type II Cepheids are dimmer than classical Cepheids, with the same pulsation period. If you mistake a Type II Cepheid for a classical Cepheid, you'll think it's farther away than it really is because it looks dimmer than expected. Hubble made this mistake systematically, so his distance measurements were too large. Since he thought galaxies were farther away than they really were, and he measured their recession velocities correctly, he calculated a Hubble constant that was too large. Over the following decades, astronomers refined the measurement. In the 1950s, Walter Baade recognized the different types of Cepheids and corrected for them. The Hubble constant dropped to around 250 kilometers per second per megaparsec. Still too high, but getting better. Alan Sandage spent much of his career improving distance measurements using multiple techniques. By the 1970s, estimates ranged from about 50 to 90 kilometers per second per megaparsec. The uncertainty was large because measuring cosmic distances is extraordinarily difficult. Every technique has potential systematic errors that can throw off your answer. In the 1990s, the Hubble Space Telescope Key project set out to measure the Hubble constant to within 10% accuracy. The team used the Space Telescope to observe Cepheid variables in distant galaxies, free from the blurring effects of Earth's atmosphere. They measured distances to galaxies out to about 65 million light-years and used those distances to calibrate other distance indicators like Type I, a supernovae. By 2001, they published their final result, 72 kilometers per second per megaparsec, plus or minus 8%. This was a triumph. After decades of uncertainty, astronomers seemed to have pinned down one of the most fundamental numbers in cosmology. But there was another way to measure the Hubble constant, a completely independent method that didn't rely on distance ladders or Cepheid variables or any observations of nearby stars. This method used the cosmic microwave background. The cosmic microwave background, usually shortened to CMB, is the afterglow of the Big Bang itself. When the universe was about 380,000 years old, it cooled enough for electrons and protons to combine into neutral hydrogen atoms. Before this moment, the universe was opaque, filled with free electrons that scattered light constantly. After this recombination, the universe became transparent. Light could travel freely through space. The light that was released at that moment has been traveling through space ever since, stretched by cosmic expansion from visible light into microwave radiation. We can detect this radiation today coming from every direction in the sky. It's remarkably uniform, with a temperature of about 2.725 Kelvin, just a few degrees above absolute zero, but it's not perfectly uniform. There are tiny variations, about 1 part in 100,000, where some regions are slightly warmer and others slightly cooler. These variations are incredibly important. They're the seeds of all structure in the universe. Slightly denser regions became the cores of galaxy clusters. Slightly less dense regions became the voids between clusters. We've mapped these temperature variations with satellite observatories. The Wilkinson Microwave Anisotropy Probe, WMAP, operated from 2001 to 2010. The Planck satellite operated from 2009 to 2013 and produced the most detailed map of the CMB ever made. From these maps, cosmologists can extract an enormous amount of information about the universe. The pattern of temperature variations depends on the universe's composition, its geometry, its age, and its expansion rate. You can think of the CMB like a cosmic sonogram, a snapshot of the universe when it was just an infant, and from that snapshot, we can deduce fundamental properties. The way this works involves sophisticated physics and mathematics, but the basic idea is straightforward. Sound waves propagated through the early universe's hot plasma. These sound waves had a characteristic size scale, determined by how far sound could travel in 380,000 years. This scale shows up in the CMB temperature variations as a characteristic angular size. By measuring this angular size and knowing the physical size scale from theory, you can calculate how far away the CMB surface is. This tells you about the geometry and expansion history of the universe. The Planck satellite's final results, published in 2018, gave a Hubble constant of 67.4 kilometers per second per megaparsec, with an uncertainty of only about 0.5%. This is extraordinarily precise. It's one of the most accurately measured numbers in all of cosmology. But there's a problem. This number disagrees with measurements made using the distance ladder method. Remember the Hubble Space Telescope Key Project result from 2001? That was 72 kilometers per second per megaparsec. The difference was about 7%, and at the time, with uncertainties of around 8% for the distance ladder and 4% for the CMB, the measurements overlapped within their error bars. It was assumed that as measurements improved, the two methods would converge. They didn't. Adam Rees, who won the Nobel Prize in 2011 for discovering that the universe's expansion is accelerating, has led efforts to improve distance ladder measurements using the Hubble Space Telescope and now the James Webb Space Telescope. His team's most recent results give a Hubble constant of about 73 kilometers per second per megaparsec, with an uncertainty of less than 2%. The Planck result is 67.4, with an uncertainty of less than 1%. These measurements don't overlap. The difference is about 8%, and both measurements are so precise that the disagreement is statistically significant at more than 5 sigma. In particle physics, 5 sigma is the gold standard for declaring a discovery. It means there's less than a 1 in 3.5 million chance that the result is a statistical fluke. So this isn't just noise. Both measurements are precise and mutually incompatible. One of them is wrong, or something deeper is going on. This is what cosmologists call the Hubble tension. Let's understand what each method actually measures and why they might disagree. The distance ladder method, championed by Rees and his collaborators, builds up distances step by step. First, you measure distances to nearby stars using geometric parallax. As Earth orbits the Sun, nearby stars appear to shift position relative to more distant background stars. The angle of this shift tells you the distance. The European Space Agency's Gaia satellite has measured parallaxes for over 1 billion stars with unprecedented precision. Using these parallax distances, you calibrate the Cepheid period luminosity relationship. Now you can use Cepheids to measure distances to nearby galaxies out to about 130 million light-years. In those galaxies, you look for Type 1, a supernovae. These are exploding white dwarf stars that reach remarkably consistent peak brightnesses. When a white dwarf in a binary system accretes enough matter from its companion to exceed about 1.4 solar masses, carbon fusion ignites explosively, and the entire star detonates. Because they all explode at nearly the same mass, they all reach similar peak luminosities. You can see Type 1 as supernovae out to billions of light years, far beyond where you can detect individual Cepheids. By observing supernovae in galaxies where you've also measured the distance using Cepheids, you calibrate how bright supernovae truly are. Then you can use supernovae to measure distances to galaxies billions of light years away. At those distances, you also measure the galaxy's redshift, how much its light has been stretched by cosmic expansion. The relationship between distance and redshift tells you the expansion rate, the Hubble constant. This method is direct and geometric. Parallax is pure trigonometry. Cepheids and supernovae are empirically calibrated using observed relationships. You're building a ladder from nearby to distant, each rung calibrated using the one below it. The cosmic microwave background method works completely differently. Here, you're not measuring distances directly at all. Instead, you're fitting a theoretical model to observed data. The model is called lambda CDM, short for lambda cold dark matter. Lambda represents dark energy, the mysterious component that makes up about 68% of the universe's total energy content and causes cosmic expansion to accelerate. Cold dark matter represents the invisible matter that makes up about 27% of the universe. Regular matter, everything we can see, is only about 5%. Lambda CDM makes specific predictions about what the CMB temperature variations should look like. The predictions depend on several parameters, including the Hubble constant, the matter density, the dark energy density, and the amount of ordinary matter. You measure the CMB, calculate its statistical properties, and find the combination of parameters that best matches your observations. When Planck did this, it found that a Hubble constant of 67.4 kilometers per second per megaparsec, combined with specific values for the other parameters, gives the best fit to the data. This is a model-dependent measurement. You're assuming lambda CDM is correct and finding the parameters that make it match observations. If lambda CDM is wrong or incomplete, your inferred Hubble constant could be wrong. The distance ladder, by contrast, is relatively model-independent. You're measuring geometric distances and redshifts, and directly calculating the expansion rate. So there are several possible explanations for the tension. First, maybe one of the measurements has a systematic error. Systematic errors are mistakes or biases in your measurement process that consistently push your answer in one direction. They're different from random errors, which average out if you make enough measurements. For the distance ladder, possible systematic errors include problems with Cepheid distance measurements. Maybe there's dust between us and the Cepheids that dims their light and makes them appear more distant than they really are. Teams have worked hard to account for dust, measuring it using infrared observations and multi-wavelength photometry. The consensus is that dust can't explain the discrepancy. Maybe the Cepheids in distant galaxies have slightly different compositions than nearby Cepheids, making them intrinsically dimmer or brighter. This is called metallicity dependence, because astronomers refer to all elements heavier than helium as metals. Studies have found small metallicity effects, but not large enough to resolve the tension. Maybe Type 1, as supernovae, aren't as uniform as we thought. Perhaps there are subtle differences depending on the galaxy's properties or the local environment. Extensive studies have characterized supernova variations. The remaining scatter after corrections is too small to account for the Hubble tension. For the CMB measurement, possible systematic errors include uncertainties in the theoretical modeling. Maybe the equations used to calculate the expected CMB pattern are missing some subtle effect. The calculations involve solving Einstein's equations for the expanding universe and computing how sound waves behave in the hot plasma of the early universe. These calculations have been checked and rechecked by independent groups using different numerical methods. They're robust. Maybe there's foreground contamination. Dust in our own galaxy emits microwave radiation that could mimic or obscure the CMB signal, Planck observed at multiple frequencies, specifically to identify and remove foreground contamination. The cleaned CMB maps agree with expectations. Maybe there are unknown instrumental effects. Satellite instruments are complicated, and there's always a possibility of subtle calibration errors. Both WMAP and Planck observed the CMB independently, using different instrument designs. They got consistent results. After years of scrutiny, neither measurement shows obvious systematic errors large enough to explain the tension. The second possibility is that both measurements are correct, but they're measuring different things. This sounds strange, but it's possible because the universe isn't perfectly homogeneous. The distance ladder measures the local expansion rate, the Hubble constant in our cosmic neighborhood within a few billion light-years. The CMB measures the expansion rate averaged over the entire observable universe based on conditions 13.8 billion years ago. If the local universe is expanding slightly faster than the cosmic average, both measurements could be correct. Why would the local universe expand faster? One possibility involves what's called a local underdensity. If we happen to live in a region where the matter density is slightly lower than average, a sort of cosmic void, the expansion rate could be locally higher. Matter slows cosmic expansion through gravity. Less matter means less gravitational braking, so expansion proceeds faster. But simulations show that to explain the Hubble tension this way, we'd need to be near the center of an enormous underdense region, hundreds of millions of light-years across. Observations suggest there's no such large-scale underdensity. Our local universe looks fairly typical. The third and most exciting possibility is that our cosmological model is incomplete or wrong. Maybe there's new physics we don't understand yet. This is where things get really interesting. One idea involves dark energy changing over time. In standard lambda CDM, dark energy has a constant density. As the universe expands and matter becomes more dilute, dark energy's relative importance increases, but its density per unit volume stays constant. This is weird. As space expands and creates more volume, there's more total dark energy. It's as if empty space has an intrinsic energy density. But maybe dark energy isn't constant. Maybe it was stronger in the early universe and has been weakening over time. Or maybe it's been growing stronger. If dark energy has evolved, the expansion history of the universe would be different from what lambda CDM predicts. The CMB measurement assumes lambda CDM with constant dark energy. If dark energy has actually been changing, the real expansion rate today could be different from what the CMB implies. This is testable. Different dark energy models make different predictions about cosmic expansion at intermediate times, several billion years ago. By measuring distances to objects at those intermediate times and comparing to redshifts, we can map the expansion history. So far, observations are consistent with constant dark energy, but there's room for subtle variations. And recently, some intriguing hints have emerged from a project called DESI, the Dark Energy Spectroscopic Instrument. DESI is mapping the three-dimensional structure of the universe by measuring distances to millions of galaxies and quasars. In 2024 and 2025, DESI released results that have cosmologists paying very close attention. The data suggests, though doesn't definitively prove, that dark energy might not be constant after all. According to DESI's measurements, there are hints that dark energy's influence could be changing over time. Specifically, the data shows a preference for models where dark energy was stronger in the past and has been weakening. This is based on observations of baryon acoustic oscillations, essentially sound waves from the early universe that left an imprint on how galaxies are distributed today. When DESI's measurements are combined with cosmic microwave background data and supernova observations, the standard model struggles to fit all the data simultaneously. But a model where dark energy evolves over time seems to work better. The significance reached about 4 sigma in their most recent analysis, which means there's roughly a 1 in 15,000 chance. This is just statistical noise. That sounds impressive, but in physics, the gold standard for a discovery is 5 sigma, about 1 in 3.5 million. So we're tantalizingly close to something significant, but not quite there yet. The DESI collaboration is appropriately cautious. They emphasize that this is early data, just the first 3 years of a 5-year survey. More observations are coming, and the picture could change. It's also possible that there are subtle systematic errors in the measurements that haven't been identified yet. But if this hint holds up, if dark energy really is evolving, the implications are profound. The universe is expanding, and that expansion is speeding up. But recent, complex data suggests the rate of that acceleration might be changing, leading to active scientific research and evolving theories. Some analyses of the DESI data even suggest that the acceleration itself might be slowing down, though this is extremely controversial and far from confirmed. If true, this would mean the universe's expansion, while still accelerating, is doing so less vigorously than it was in the past. In the very far future, if this trend continued, gravity could potentially overcome dark energy, and the expansion could transition from acceleration to deceleration. This opens up possibilities for the universe's ultimate fate that we thought were closed. Instead of expanding forever into cold, dark emptiness, maybe the universe's fate is more complex, more interesting, or maybe none of this is real. Maybe it's all measurement error or statistical fluctuation that will vanish with more data. That's the nature of cutting-edge science. You're working at the boundary of knowledge where nothing is certain yet. The DESI results are exciting precisely because they're uncertain. They point towards something unexpected, something that challenges our standard model. But they don't prove it yet. Over the next few years, as DESI completes its survey and other experiments add their data, we'll learn whether this hint of evolving dark energy is real or a mirage. For now, it adds another layer of complexity to the Hubble tension. Maybe dark energy evolution is connected to why our measurements disagree. Maybe it's a separate mystery entirely. Or maybe it will help resolve the tension by pointing toward the missing physics in our models. Another idea involves early dark energy, a hypothetical component that existed in the early universe but has since decayed away. This would affect the physics of the early universe when the CMB was formed, changing the relationship between the CMB's acoustic features and the Hubble constant. Models with early dark energy can simultaneously fit both the CMB and the distance ladder data. But they require introducing new physics, a new energy component that we have no independent evidence for. Scientists are cautious about adding new components just to fix a discrepancy, but if the tension persists and other explanations fail, early dark energy becomes more plausible. A third idea involves extra-relativistic particles in the early universe. The standard model of particle physics includes 3 types of neutrinos. These are nearly massless particles that interact very weakly with matter. They were abundant in the early universe and contributed to its energy density. What if there are additional neutrino species we haven't detected yet, or other light particles? Extra radiation in the early universe would affect the CMB in specific ways. changing the inferred Hubble constant. Adding extra radiation can reduce the tension between CMB and distance ladder measurements, but particle physics has no strong motivation for additional neutrino species beyond the three we know. We'd need new physics beyond the standard model. Perhaps the most radical idea is that our understanding of gravity itself is incomplete. General relativity has passed every test so far, but maybe at cosmic scales or in certain regimes, modifications are needed. Modified gravity theories can alter cosmic expansion in ways that might reconcile the measurements. But any modification must be very subtle because general relativity works so well in other contexts. You can't just throw out general relativity. You have to propose a modification that keeps all the successful predictions while fixing the Hubble tension. That's a tall order. None of these ideas has gained widespread acceptance yet, because none has strong independent evidence. They're motivated primarily by the desire to resolve the Hubble tension. Scientists are inherently suspicious of explanations that seem ad hoc, invented specifically to fix one problem without broader motivation. So where does that leave us? We have two measurements that should agree but don't. The disagreement is statistically significant and has persisted despite years of effort to find systematic errors or resolve the tension. Neither measurement seems obviously wrong. The most conservative position is to wait for more data. New observatories and new techniques might break the deadlock. The James Webb Space Telescope is measuring Cepheid variables and calibrating the distance ladder with unprecedented precision. Its infrared cameras can see through dust better than Hubble's optical cameras, potentially reducing uncertainties from dust extinction, and the results have been fascinating. In February 2024, JWST observations confirmed that Hubble's Cepheid measurements were accurate. The tension wasn't due to errors in Hubble's data. By December 2024, Adam Rees's team had analyzed JWST observations of over 320 Cepheids in multiple galaxies. JWST's higher resolution reduced the scatter in Cepheid measurements by more than 2.5 times compared to Hubble. All galaxies observed by JWST, combined with their supernovae, yielded a Hubble constant of 72.6 kilometers per second per megaparsec, nearly identical to Hubble's value of 72.8 kilometers per second per megaparsec for the same galaxies. This ruled out systematic errors in Hubble's measurements at very high confidence. But here's where it gets interesting. Another team, led by Wendy Friedman, also using JWST, got a different result. Friedman's group used different distance indicators, the tip of the red giant branch and J-region asymptotic giant branch stars, instead of Cepheids. These stars are older and found in different parts of galaxies, away from the crowded, dusty regions where Cepheids live. When Friedman's team measured distances using these stars, they found a Hubble constant between 68.4 and 71.5 kilometers per second per megaparsec, intermediate between the CMB and Cepheid values. Their best estimate was around 69 to 70 kilometers per second per megaparsec. So even with the same telescope, JWST, different teams using different methods are getting different answers. The Cepheid method gives about 73. The red giant method gives about 69 to 70. The CMB gives about 67. None of these are quite compatible within their uncertainties. This suggests the problem is more subtle than just systematic errors in one particular technique. Maybe there are complexities we don't understand about how these different stellar populations work as distance indicators. Maybe there's something about dust or stellar evolution that affects the measurements in ways we haven't fully accounted for. The tension remains. Future CMB experiments might provide more precise maps or probe different aspects of the early universe that could reveal systematics in the current measurements. Gravitational wave astronomy offers a completely independent way to measure cosmic distances. When two neutron stars or black holes merge, they emit gravitational waves, ripples in space-time itself. The amplitude of these waves tells you the distance to the source. If you also identify the host galaxy with traditional telescopes and measure its redshift, you have both distance and recession velocity. This gives a direct measurement of the Hubble constant without relying on the distance ladder or the CMB. So far, gravitational wave measurements have large uncertainties because we've only detected a limited number of events. But as more detectors come online and we detect more mergers, the precision will improve within a decade or two. Gravitational waves might provide a decisive measurement that either agrees with one of the existing methods or points to something entirely new. Strong gravitational lensing offers another approach. When a massive galaxy lies between us and a distant quasar, the galaxy's gravity bends light from the quasar, creating multiple images. Light taking different paths around the lens arrives at different times. If the quasar brightens or dims, we see the change in one image first, then later in the other images. By measuring these time delays and modeling the lensing galaxy's mass distribution, you can calculate the distance to the quasar and infer the Hubble constant. This method is independent of both the distance ladder and the CMB. The TD Cosmo collaboration has been using this technique with increasing precision. In December 2025, they published results using 8 carefully studied gravitationally lensed quasar systems. Their measurement gave a Hubble constant of about 73 kilometers per second per megaparsec, with uncertainty of about 3%. This agrees with the distance ladder measurements and disagrees with the CMB. So gravitational lensing, which is completely independent of Cepheids and supernovae, is confirming the higher value. This strengthens the case that the tension is real, not just a problem with one particular measurement technique. But lensing measurements have their own challenges. You need to model the mass distribution of the lensing galaxy very carefully. If your model is wrong, your distance is wrong. Different modeling assumptions can shift the results. So, while the lensing measurements are encouraging, they're not yet definitive. More lenses need to be studied to improve precision and test for systematic effects. The tension has energized the cosmology community. It's forced researchers to scrutinize their methods and assumptions more carefully than ever before. It's driven the development of new observational techniques and better theoretical models. And it's created a sense of anticipation. Everyone knows that something interesting is going on. Either we'll find a subtle, systematic error and the tension will resolve, which would be satisfying but a bit anticlimactic. Or we'll confirm that both measurements are correct and our cosmological model is wrong or incomplete, which would be revolutionary. New physics is always exciting because it opens doors to understanding aspects of nature we didn't even know we were missing. Think about what dark energy represents. It's about 68% of the universe's total energy content, and we have no idea what it is. We know it causes cosmic expansion to accelerate, but we don't know its fundamental nature. Is it Einstein's cosmological constant, a property of empty space itself? Is it a dynamic field that can change over time? Is it a sign that general relativity breaks down at cosmic scales? Resolving the Hubble tension might point us toward the answer. The same goes for dark matter. We know it exists from its gravitational effects, but we don't know what particles it's made of. We've built sensitive detectors to try to catch dark matter particles interacting with normal matter. We've accelerated particles to high energies, hoping to create dark matter in collisions. So far, nothing. Dark matter remains mysterious. Maybe the Hubble tension is telling us something about dark matter's properties or its role in cosmic evolution. And then there's gravity itself. General relativity is one of the most successful scientific theories ever developed. It's passed every test we've thrown at it, from the precession of Mercury's orbit to the detection of gravitational waves, but we know it's incomplete. It doesn't play well with quantum mechanics. At the center of black holes, general relativity predicts singularities, points where gravity becomes infinite and the equations break down. Nobody believes singularities are real, physical objects. They're signs that our theory is failing, that we need a quantum theory of gravity to describe what really happens. String theory, loop quantum gravity, and other approaches have tried to quantize gravity, but none has succeeded in making testable predictions yet. Maybe the Hubble tension is a hint. Maybe at cosmic scales, quantum effects in gravity become important in ways we haven't anticipated. This might sound like wild speculation, and to some extent it is, but science progresses by taking unexplained observations seriously and following where they lead. The cosmic microwave background itself was discovered accidentally in 1964 by Arno Penzias and Robert Wilson. They were trying to eliminate noise from a radio antenna and kept detecting a persistent signal from all directions in the sky. They initially thought it was interference from pigeon droppings on the antenna. After cleaning it thoroughly and finding the signal unchanged, they realized they were detecting something cosmological. It turned out to be the CMB, the afterglow of the Big Bang, predicted theoretically but never observed. The discovery won them the Nobel Prize and confirmed the Big Bang theory. An unexpected observation led to a revolution in our understanding of the universe. The accelerating expansion of the universe, the discovery of dark energy, came from observations in 1998 that were also unexpected. Two teams were studying distant Type 1, a supernovae, to measure how cosmic expansion was slowing down. Everyone expected the expansion to be decelerating due to gravity. Instead, the supernovae appeared dimmer than expected, indicating they were farther away than standard cosmology predicted. The universe's expansion was speeding up, not slowing down. This was shocking. It implied a new component of the universe, dark energy, pushing space apart. It won the 2011 Nobel Prize. Another unexpected observation, another revolution. The Hubble tension might be the next one. Or it might fizzle. That's the nature of science. You follow promising leads. Some pan out, some don't. But right now, this is one of the most important unsolved problems in cosmology. Let's zoom out and think about what this all means for our understanding of the universe. When Hubble discovered cosmic expansion in 1929, it fundamentally changed how we view our place in the cosmos. The universe had a beginning. It's been evolving ever since. It has a history. Before this, the prevailing view was that the universe was eternal and static, unchanging on the largest scales. Cosmic expansion overturned this. Run the expansion backward in time, and you find that the universe was once much smaller, denser, and hotter. Go back far enough, and you reach the Big Bang, the moment when space and time themselves began about 13.8 billion years ago. This gives the universe an age. It means everything we see, all the galaxies, stars, and planets, formed from an initially smooth, hot plasma that cooled and condensed over billions of years. It means the universe hasn't always looked like it does now and won't always look like it does in the future. In the far future, as cosmic expansion continues accelerating, galaxies beyond our local group will be carried away beyond our observable horizon. The observable universe will shrink from our perspective. Eventually, in trillions of years, observers in the Milky Way, or whatever galaxy results from the merger of the Milky Way and Andromeda, will look out and see only their own galaxy and a handful of small satellites. All other galaxies will be so distant that their light can no longer reach us. Civilizations arising at that time would have no way to discover the Big Bang or the expansion of the universe. They'd be observationally cut off from understanding cosmic history. We're fortunate to live at a time when we can still observe the broader universe, when the evidence for the Big Bang is still accessible. The Hubble constant tells us not just how fast the universe is expanding now, but also how old it is. If you know the expansion rate and how it's changed over time, you can calculate when the expansion began, the age of the universe. That's why precision measurements of the Hubble constant matter. They refine our understanding of cosmic history. The current best estimate for the universe's age is about 13.8 billion years. This comes primarily from CMB measurements. If the true Hubble constant is higher, closer to the distance ladder value, the universe would be younger, maybe 12.5 or 13 billion years. That might create problems. We've dated the oldest stars in globular clusters using stellar evolution models. They appear to be about 13 billion years old, some estimates even slightly older. The universe can't be younger than its oldest stars. So a higher Hubble constant creates tension not just between measurement methods but also with stellar ages. Resolving the Hubble tension might require rethinking how we date stars or how we model stellar evolution. It all connects. The Hubble constant also relates to the universe's fate. Is it going to expand forever, or will it eventually stop and collapse back in a big crunch? The answer depends on the total energy density of the universe compared to a critical value. If the density is above critical, gravity will eventually halt and reverse the expansion. If it's below critical, the universe expands forever. Observations suggest the universe is almost exactly at the critical density, a flat universe where parallel lines remain parallel forever. But there's dark energy causing accelerated expansion. As long as dark energy continues to dominate, the universe will expand forever, becoming increasingly cold, dark, and empty. Stars will burn out. Galaxies will evaporate as stars are ejected through gravitational interactions. Black holes will slowly evaporate through Hawking radiation. Eventually, in 10 to the 100 years or more, the universe will reach a state of maximum entropy, a cold equilibrium where nothing interesting happens. This is called the heat death of the universe. It's the ultimate consequence of the second law of thermodynamics combined with eternal cosmic expansion. Not exactly cheerful, but that's billions of trillions of years in the future. For now, the universe is young and vibrant. Stars are forming, galaxies are colliding and merging, black holes are growing, and we're here trying to understand it all. The Hubble tension reminds us how much we still don't know. For all our sophisticated telescopes and theoretical models, we're still puzzled by basic questions about the universe's expansion rate. This is humbling, but it's also exciting. Science isn't a collection of facts. It's a process of questioning, testing, refining, and occasionally overturning what we thought we knew. The best scientists are comfortable with uncertainty and excited by unexplained observations, because those are opportunities to learn something new. Let's talk about some of the specific observations that have sharpened the Hubble tension. Adam Rees and his collaborators have used the Hubble Space Telescope to observe Cepheid variables in galaxies hosting Type 1, a supernovae. By 2022, they had measured Cepheids in 42 galaxies, calibrating the supernova brightness with unprecedented precision. Their result was 73.04 kilometers per second per megaparsec, with an uncertainty of only 1.4%. That's remarkably precise. They've also used the James Webb Space Telescope to observe more distant Cepheids. JWST's infrared sensitivity allows it to penetrate dust better than Hubble and to see Cepheids in galaxies beyond Hubble's reach. Early results from JWST have confirmed the distance ladder measurements, finding similar Hubble constant values. Meanwhile, cosmologists analyzing the CMB have refined their measurements. The Planck satellite's final data release in 2018 gave 67.36 kilometers per second per megaparsec, with an uncertainty of less than 1. Subsequent analyses using different methods to account for foreground contamination and systematic effects have confirmed this value. The Atacama Cosmology Telescope, a ground-based CMB observatory in Chile, has independently measured the CMB and found results consistent with Planck. So both sides of the tension have been reinforced by new, independent observations. This makes the disagreement more, not less, puzzling. Some researchers have looked for clues in intermediate distance measurements. There are techniques that work at distances between where Cepheids can be observed and where the CMB probes. One such technique uses the tip of the red giant branch, a feature in the color magnitude diagram of old stellar populations. Red giant stars reach a maximum luminosity before transitioning to later evolutionary stages. This maximum luminosity is fairly uniform across different stellar populations. By measuring the apparent brightness of the tip of the red giant branch in a galaxy, you can infer its distance. This method is independent of Cepheids and has been used to calibrate Type 1 supernovae distances. Results from this method give Hubble constant values around 70 kilometers per second per megaparsec, intermediate between the CMB and distance ladder values. Some researchers interpret this as a hint that the truth lies somewhere in the middle, but the uncertainties are still large. Another approach uses surface brightness fluctuations. Galaxies are made of stars, and when you look at a distant galaxy that can't be resolved into individual stars, the galaxy appears smooth. But there are subtle pixel-to-pixel brightness variations due to the fact that some pixels contain slightly more or fewer stars by chance. The amplitude of these fluctuations depends on distance. Closer galaxies have larger fluctuations. By measuring the fluctuations and calibrating them using galaxies at known distances, you can measure distances to other galaxies. This technique has also been used to measure the Hubble constant, with results generally falling on the higher end, closer to the distance ladder value. The variety of methods is actually a strength of modern cosmology. No single technique is beyond question. Every technique has assumptions and potential systematics. But when multiple independent techniques agree, confidence grows. Right now, we're in a situation where different techniques disagree, which means we need to dig deeper. It's worth stepping back and appreciating just how remarkable it is that we can measure the universe's expansion rate at all. A century ago, we didn't even know the universe was expanding. We didn't know about other galaxies. We didn't know the universe had a finite age. Now we can measure its expansion rate to a precision of a few percent and argue about whether it's 67 or 73 kilometers per second per megaparsec. That's extraordinary progress. And we're doing it with light. Photons that have traveled across the universe for billions of years, carrying information about the objects that emitted them. By analyzing these photons, measuring their wavelengths, their arrival times, their polarization, we reconstruct the history and structure of the cosmos. Every photon is a messenger from the distant universe. The CMB photons we detect today were emitted when the universe was 380,000 years old. They've been traveling for 13.8 billion years, stretched by cosmic expansion from visible light into microwaves. When we map the CMB, we're seeing a snapshot of the infant universe, a time when no stars or galaxies existed yet, when everything was a hot, glowing plasma on the verge of condensing into the structures we see today. The photons from distant supernovae tell us about stars that exploded billions of years ago in galaxies far across the universe. They tell us how bright those explosions were, how fast the galaxies were receding, how the universe was expanding at that earlier time. And the photons from Cepheid variables tell us about pulsating stars in nearby galaxies. Stars that have since continued pulsating, or perhaps evolved off the main sequence and died. All this information, encoded in light, That's the beauty of astronomy. We can't visit these distant places. We can't travel back in time to see the early universe directly. But we don't need to. The information comes to us, carried by photons that have journeyed across the cosmos. Our job is to collect those photons and decode their message. That's what telescopes do. They're time machines, showing us the universe as it was in the past. The farther away you look, the farther back in time you see. The Andromeda Galaxy is about 2.5 million light-years away. When you look at Andromeda, you see it as it was 2.5 million years ago. If something happened there yesterday, we won't know about it for 2.5 million years. Some of the galaxies we observe are billions of light-years away. We're seeing them as they were billions of years ago, when the universe was much younger. Those galaxies today might look completely different. They might have merged with other galaxies, or formed new stars, or had their gas stripped away. We'll never know. We can only see them as they were in the ancient past. This makes cosmology fundamentally historical. We're studying the history of the universe by observing its past, and the expansion of the universe adds another layer. Not only are we seeing distant objects as they were long ago, but the space between us and them has stretched since the light was emitted. A galaxy whose light has been traveling for 10 billion years isn't 10 billion light-years away. It's farther, because the space between us and the galaxy has expanded during those 10 billion years. The relationship between light, travel time, and actual distance depends on the expansion history, which depends on the Hubble constant and the universe's composition. This is why cosmology is so intertwined. Every measurement connects to every other measurement. The Hubble constant affects distance calculations, which affect determinations of the universe's geometry, which affect estimates of dark energy density, which affect predictions for future expansion. It's all one big, interconnected web. Pull on one thread, and everything else shifts. That's why the Hubble tension is so consequential. It's not just about one number. It's about the entire framework we use to understand the universe. Some physicists have proposed that the solution involves rethinking how we do cosmology. Maybe we need to be more careful about averaging over the universe's structure. The universe isn't perfectly smooth. It has galaxies, clusters, voids, and superclusters. On very large scales, these average out, and the universe looks homogeneous. But maybe the averaging isn't as straightforward as we thought. Maybe there are subtle effects from structure that bias our measurements in ways we haven't accounted for. This is an active area of research. Computer simulations model how structure forms and evolves and how light propagates through the lumpy universe. So far, these effects appear to be small, too small to explain the Hubble tension. But the calculations are complex and ongoing. Another possibility is that we're making incorrect assumptions about initial conditions. The standard cosmological model assumes the early universe was very close to homogeneous and isotropic, the same in all places and in all directions. Tiny quantum fluctuations seeded the structure we see today, but the average was extremely smooth. What if the early universe was less smooth than we think? What if there were larger scale variations that we haven't accounted for? This could affect how we interpret the CMB and how we extrapolate from the early universe to the present day. But observations of the CMB suggest the early universe was incredibly smooth, with variations of only 1 part in 100,000. Any deviation from this would show up in the data. So far, the data looks consistent with a very smooth early universe. There's also been discussion about whether the fundamental constants of nature might have changed over time. Constants like the speed of light, the gravitational constant, or the fine structure constant are assumed to be truly constant, the same at all times and places. But what if they're not? What if they were slightly different in the early universe? This would affect everything: the way atoms behave, the way light propagates, the way gravity works. The CMB and distance ladder measurements would be affected differently, potentially explaining why they disagree. But there's no independent evidence for changing constants. Laboratory experiments have set stringent limits on how much these constants could vary. Astronomical observations of distant quasars, whose light has traveled billions of years to reach us, show that atoms behaved the same way in the distant past as they do today. The fine structure constant, which governs electromagnetic interactions, appears to be constant to within a few parts per million over cosmic time. So while changing constants is theoretically possible, there's no strong observational support for it. It remains a speculative idea. What's needed is a decisive observation that clearly favors one explanation over others. Maybe JWST will find that Cepheid distances have been systematically wrong due to some previously unrecognized effect. Maybe future CMB experiments will find that foreground contamination was more significant than thought, biasing the Planck results. Maybe gravitational wave observations will clearly agree with one method and rule out the other. Or maybe multiple independent techniques will all converge on a Hubble constant value that's different from both the CMB and distance ladder results, pointing to something entirely unexpected. The next decade will be critical. New observatories are coming online, new techniques are being developed, and the data will keep getting better. Eventually, the truth will emerge. That's how science works. You gather evidence, you test hypotheses, you refine measurements, and slowly, the picture becomes clearer. Sometimes it takes decades. The existence of dark matter was proposed in the 1930s by Fritz Zwicky based on observations of galaxy clusters. He found that galaxies in clusters were moving too fast to be held together by the gravity of their visible matter alone. There had to be additional unseen mass. But dark matter wasn't widely accepted until the 1970s and 80s, when Vera Rubin and others measured the rotation curves of galaxies and confirmed that dark matter was necessary to explain the observations. Even then, alternative theories like modified gravity were proposed to explain the observations without dark matter. It wasn't until the 1990s and 2000s, with observations of gravitational lensing, the cosmic microwave background, and large-scale structure, that dark matter became the consensus explanation. It took 70 years to go from initial evidence to firm acceptance. Dark energy was even faster. Proposed in 1998, based on supernova observations, it's now a cornerstone of the standard cosmological model, but we still don't know what it is. The Hubble tension might follow a similar trajectory. Recognized as significant around 2015. When improved measurements made it clear the disagreement wasn't going away, it's now one of the top priorities in cosmology. Within a decade or two, we might look back and see it as the moment when we realized our cosmological model needed revision. Or we might look back and see it as a measurement challenge that was eventually resolved by better data and more careful analysis. Either way, it's an exciting time to be studying the universe. We're at the frontier of knowledge, grappling with observations that don't quite fit, exploring new ideas, building new instruments. This is science at its best. Not a finished edifice of knowledge, but a dynamic process of discovery. Let's talk about what the Hubble constant actually means in more intuitive terms. We've been discussing it as a number, 67 or 73 kilometers per second per megaparsec. But what does this mean for the universe? Imagine two galaxies separated by 1 megaparsec, about 3.26 million light-years. If the Hubble constant is 70 kilometers per second per megaparsec, those galaxies are receding from each other at 70 kilometers per second due to cosmic expansion, not moving through space, but being carried apart by the expansion of space itself. Now imagine two galaxies twice as far apart, 2 megaparsecs. They're receding at 140 kilometers per second. 10 megaparsecs apart, 700 kilometers per second. 100 megaparsecs, 7,000 kilometers per second, about 2% of the speed of light. 1,000 megaparsecs, 70,000 kilometers per second, about 23% of the speed of light. The recession velocity keeps increasing with distance. At large enough distances, the recession velocity exceeds the speed of light. This doesn't violate relativity because the galaxies aren't moving through space faster than light. Space itself is expanding, and there's no limit on how fast space can stretch. The observable universe has a radius of about 46 billion light-years. Galaxies at that distance are receding from us at velocities much greater than the speed of light. Their light can still reach us because the light is traveling through space toward us, even though space is expanding, carrying the galaxies away. It's like swimming upstream. If the current is faster than you can swim, you're carried downstream, but you're still making progress through the water. Photons from distant galaxies are traveling toward us through space that's expanding. If the expansion is too fast, the photons never reach us. There's a cosmic horizon beyond which we can never see. Galaxies beyond that horizon are receding faster than light can approach us, so their light will never arrive. The Hubble constant determines where this horizon lies. A higher Hubble constant means faster expansion, a closer horizon, a smaller observable universe. A lower Hubble constant means slower expansion, a more distant horizon, a larger observable universe. The difference between 67 and 73 kilometers per second per megaparsec translates to a difference in the size and age of the universe. It affects how we understand cosmic history, the formation of structure, and the future evolution of the cosmos. That's why precision matters. We're not arguing over an obscure detail. We're arguing over the fundamental parameters that define our universe. Think about the effort that's gone into these measurements. The Hubble Space Telescope has observed Cepheid variables in dozens of galaxies, requiring hundreds of hours of precious telescope time. Each observation must be carefully planned, executed, and analyzed. The Planck satellite operated for years, scanning the entire sky repeatedly in 9 frequency bands to map the cosmic microwave background with exquisite precision. The data processing and analysis took thousands of hours of supercomputer time. Teams of scientists around the world have dedicated their careers to improving these measurements. They've developed new techniques, built new instruments, and refined theoretical models, all to pin down this one number, the Hubble constant, to better and better precision. And now that they've achieved precision of a few percent, they find that different methods disagree. This is frustrating, certainly, but it's also a sign that we're pushing the boundaries of what we can measure and understand. We're not content with rough estimates. We demand precision. And when we achieve precision, we sometimes discover that things are more complicated than we thought. This has happened before in the history of science. In the late 1800s, physicists thought they understood the universe pretty well. Newtonian mechanics described motion. Maxwell's equations described electromagnetism. Thermodynamics described heat and energy. But there were a few nagging problems. The orbit of Mercury didn't quite match predictions. Blackbody radiation didn't behave as classical physics predicted. The speed of light appeared to be the same for all observers, contradicting expectations from Galilean relativity. These were small discrepancies, a few percent here, a factor of 2 there. Most physicists expected they'd be resolved with minor tweaks to existing theories. Instead, they led to quantum mechanics and general relativity, completely new frameworks that revolutionized physics. The Hubble tension might be our generation's version of those discrepancies, a small disagreement that points to something profound. Or it might not. We don't know yet. That's what makes it exciting. The process of science involves living with uncertainty, pursuing multiple lines of investigation, and being open to wherever the evidence leads. Cosmology has come so far in the past century. We've gone from not knowing whether other galaxies exist to mapping the universe on the largest scales. We've discovered the Big Bang, dark matter, dark energy, gravitational waves, exoplanets, and so much more. Each discovery has opened new questions. That's the nature of knowledge. The more you learn, the more you realize you don't know. But the questions we're asking now are deeper and more refined than the questions we were asking a century ago. We're no longer asking whether the universe is expanding. We know it is. We're asking exactly how fast it's expanding and whether that rate has changed over time in ways we haven't anticipated. We're no longer asking whether dark matter exists. We know it does. We're asking what particles it's made of and how they interact. We're no longer asking whether black holes exist. We've imaged them and detected their mergers. We're asking how they grow, how they influence galaxy evolution, and what happens at their event horizons. These are harder questions, requiring more sophisticated observations and more detailed theories. But they're also more interesting questions. They probe the fundamental nature of reality. The Hubble constant is part of this quest. It's not just a number. It's a window into how the universe works, how it began, how it evolved, and where it's headed. Getting it right matters, because everything else builds on it. If we don't understand cosmic expansion, we can't fully understand structure formation, galaxy evolution, or the fate of the universe. So cosmologists will keep measuring, analyzing, and debating until the tension is resolved. They'll build better instruments, develop new techniques, and test new ideas. Eventually, we'll have an answer. We'll know whether the Hubble constant is 67 or 73 or something else entirely. We'll know whether our cosmological model is correct or whether it needs revision. And we'll know a bit more about the universe we inhabit. That's worth the effort. Understanding the cosmos is one of humanity's greatest achievements. Not because it has practical applications, though sometimes it does, but because it satisfies our curiosity. We look up at the stars and we wonder, where did they come from? How far away are they? What are they made of? How does it all work? These are fundamentally human questions, questions we've been asking for thousands of years. Ancient cultures had their own cosmologies, stories about how the universe came to be and how it operates. They were beautiful stories, often involving gods and heroes, creation and destruction. But they weren't testable. You couldn't observe the heavens and determine whether the stories were true. Modern cosmology is different. It's based on observations and mathematics. We make predictions and test them. When observations disagree with predictions, we revise our theories. This is a more modest approach in some ways. We don't claim to have all the answers. We admit uncertainty. But it's also a more powerful approach because it allows us to learn and improve. The Hubble tension is a perfect example. We have two measurements that should agree but don't. We don't know why. We're honest about this. We don't pretend to have an answer we don't have. Instead, we keep working, keep investigating, keep gathering data. Eventually, the evidence will point us toward the truth. That's the scientific method. It's not perfect, but it's the best tool we have for understanding the natural world, and it's given us an astonishing understanding of the universe. We know the universe is 13.8 billion years old. We know it started in a hot, dense state and has been expanding and cooling ever since. We know it's made mostly of dark matter and dark energy, with ordinary matter making up only a small fraction. We know galaxies formed from tiny density fluctuations in the early universe, growing over billions of years into the majestic structures we see today. We know stars form from collapsing gas clouds, shine for millions or billions of years by fusing hydrogen into helium, and eventually die, sometimes exploding as supernovae and seeding the cosmos with heavy elements. We know planets form from disks of gas and dust around young stars, and that planets are common, probably orbiting most stars in the galaxy. We know black holes exist, that they form from the collapse of massive stars, and that supermassive black holes, millions or billions of times the Sun's mass, lurk at the centers of most galaxies. We know gravitational waves are real, that they carry energy across the universe, and that they provide a new way to observe cosmic events. All of this we've learned in the past century. It's an incredible achievement. And we're still learning. The Hubble tension is part of that ongoing learning process. It's a reminder that science is never finished. There's always more to discover, more to understand. The universe is vast and complex, and we've only scratched the surface. But every mystery we solve, every question we answer, brings us closer to a complete picture. And even when we don't have all the answers, the questions themselves are valuable. They drive us to look deeper, think harder, and build better tools. They remind us that the universe is full of wonder, full of phenomena we don't yet understand, and they give us a sense of purpose. We're part of the universe trying to understand itself. We're made of atoms, forged in the hearts of stars, organized into structures complex enough to think and wonder and ask questions about our origins. That's profound. It's also humbling. We're incredibly small on cosmic scales. The Earth is a tiny planet orbiting an average star in an ordinary galaxy among trillions of galaxies in an observable universe that might itself be just one of countless universes. We occupy a vanishingly small fraction of space and time, but we're also significant because we can understand. We can look out at the cosmos and comprehend what we see. We can measure the universe's expansion rate, debate whether it's 67 or 73 kilometers per second per megaparsec, and work to resolve the discrepancy. That ability to understand, to question, to investigate is perhaps the most remarkable thing about us. So while the Hubble tension is a scientific problem, it's also a reflection of something deeper. Our desire to understand, our refusal to accept easy answers, our commitment to following the evidence wherever it leads. These are the qualities that have allowed us to learn so much about the universe. And these are the qualities that will eventually resolve the Hubble tension and answer the many other questions that remain. The universe is expanding. We know that much for certain. We just don't know exactly how fast. But we're working on it. And one day, we'll have the answer. Until then, we keep looking up, keep measuring, keep thinking, because that's what we do. We're explorers, investigating the cosmos from our tiny vantage point on this small blue planet. And the universe, for all its vastness and mystery, is slowly revealing its secrets to us. The Hubble tension is just one more secret waiting to be uncovered, one more piece of the cosmic puzzle waiting to fall into place. And when it does, we'll understand the universe a little bit better. We'll know whether our cosmological model is correct or whether it needs revision. We'll know whether there's new physics waiting to be discovered or whether we've simply been making a subtle systematic error all along. Either way, we'll have learned something, and that's what matters. Not just getting the right answer, but the process of discovery itself, the journey of exploration, investigation, and understanding. That's what makes cosmology worthwhile. That's what makes science beautiful. Tonight, we've explored one of the biggest unsolved problems in modern cosmology, the Hubble tension, the disagreement between different measurements of the universe's expansion rate. We've seen how this tension arose, what it might mean, and why cosmologists are working so hard to resolve it. We've discussed the different measurement techniques, the cosmic microwave background and the distance ladder, and how they give different answers. We've considered possible explanations, from systematic errors to new physics, and we've reflected on what this all means for our understanding of the cosmos. The Hubble constant isn't just a number. It's a fundamental parameter that shapes our entire picture of the universe. Getting it right is crucial. And right now, we're not sure we have it right. That's okay. Science is comfortable with uncertainty. It's through uncertainty that we make progress. The Hubble tension is driving new observations, new techniques, and new ideas. Within a decade or two, we'll likely have an answer. We'll know whether the tension was real, pointing to new physics, or whether it was a measurement problem that better data and more careful analysis eventually resolved. Either way, we'll have learned something valuable, and we'll have advanced our understanding of the universe one more step. That's the beauty of cosmology. We're part of an ongoing journey of discovery, a journey that began centuries ago when humans first looked up at the night sky and wondered what they were seeing. We've come far since then. We've measured the distances to stars and galaxies. We've discovered that the universe is expanding, that it had a beginning, that it's filled with mysterious dark matter and dark energy. We've detected gravitational waves and imaged black holes, and we've learned that the universe is vast beyond comprehension, ancient beyond imagining, and still full of mysteries waiting to be solved. The Hubble tension is one of those mysteries, and solving it will bring us one step closer to understanding the true nature of the cosmos. Let me take you deeper into why this measurement is so challenging and why every percentage point matters. When Edwin Hubble made his original observations in the 1920s, he was working with the 100-inch Hooker telescope at Mount Wilson Observatory, the largest telescope in the world at that time. He could barely resolve individual stars in nearby galaxies. The photographic plates he used required long exposures, sometimes hours, to capture enough light. The measurements were crude by modern standards, subject to all kinds of errors, but they were revolutionary because they showed, for the first time, that the universe was not static. Fast forward to today. We have telescopes in space, above Earth's atmosphere, capturing images with incredible clarity. We have detectors that can count individual photons. We have computers that can process enormous amounts of data and correct for systematic effects. We have theoretical models based on general relativity and quantum mechanics that make precise predictions, and yet we still can't agree on the expansion rate to within 10%. This tells you something about the challenge. Measuring cosmic distances is hard, really hard. Every technique involves a chain of assumptions and calibrations, and small errors in one step propagate through the entire chain. Consider the distance ladder approach in detail. The first step is parallax, measuring the apparent shift of nearby stars as Earth orbits the Sun. This is pure geometry. If you know the baseline, Earth's orbital diameter of 186 million miles, and you measure the angle of shift, you can calculate the distance. Simple trigonometry. But the angles are incredibly small. The nearest star, Proxima Centauri, shows a parallax angle of 0.77 arcseconds. That's less than 1/1000th of a degree. To put this in perspective, it's like trying to measure the width of a human hair from a distance of 33 feet. For more distant stars, the angles are even smaller. A star 1,000 light-years away has a parallax of only 0.003 arcseconds. That's at the limit of what can be measured from the ground, even with the best telescopes under perfect atmospheric conditions. The European Space Agency's Gaia satellite has revolutionized parallax measurements. Launched in 2013, Gaia orbits at the L2 Lagrange point, about 930,000 miles from Earth, where it has an incredibly stable viewing platform. It carries 2 telescopes and a billion-pixel camera, the largest digital camera ever flown in space. Gaia scans the entire sky repeatedly, measuring the positions of stars with unprecedented precision. Over its mission, it has observed more than 1 billion stars multiple times each. For the brightest stars, Gaia can measure parallaxes with an uncertainty of only 10 micro-arcseconds. That's 10 millionths of a degree. It's like measuring the width of a human hair from 620 miles away. This precision allows Gaia to measure distances to stars halfway across the galaxy, tens of thousands of light-years away. That's a huge improvement over previous capabilities. But even Gaia has limits. For faint stars or very distant stars, the uncertainties grow. And parallax only works within our galaxy. You can't use parallax to measure distances to other galaxies because they're too far away. The parallax angles would be far smaller than anything we can measure. So the next step in the distance ladder is Cepheid variables. These are supergiant stars that pulsate rhythmically, brightening and dimming over periods ranging from a few days to several months. The pulsations are driven by instabilities in the star's outer layers. As the star contracts, it heats up and becomes more opaque, trapping radiation. The trapped radiation builds up pressure until it pushes the outer layers back out. As the star expands, it cools and becomes more transparent, releasing the radiation. The pressure drops, gravity takes over, and the star contracts again. This cycle repeats indefinitely, creating a very regular pattern of brightness variation. Henrietta Leavitt discovered in 1908 that the period of pulsation is related to the star's intrinsic luminosity. Brighter Cepheids pulsate more slowly. Dimmer Cepheids pulsate more quickly. The relationship is remarkably tight. If you measure the period, you can predict the luminosity with an uncertainty of only about 10 to 15%. This makes Cepheids incredibly useful as distance indicators. You observe a Cepheid, measure how long it takes to complete one pulsation cycle, and from that you know how luminous it truly is. Then you measure how bright it appears from Earth. The difference between true luminosity and apparent brightness tells you the distance. A star that's twice as far away appears 4 times dimmer, because light spreads out as it travels and the intensity falls off with the square of the distance. This is called the inverse square law. It's a fundamental property of how light propagates through space. But using Cepheids for distance measurements requires careful calibration. You need to know the exact relationship between period and luminosity, and this is where parallax comes in. For the nearest Cepheids, within a few thousand light-years, Gaia can measure distances directly using parallax. This tells you the Cepheid's true distance and true luminosity. Plot period versus luminosity for many Cepheids with known distances, and you map out the period-luminosity relationship precisely. This is the calibration. Now you can apply this relationship to more distant Cepheids, where parallax doesn't work. Measure their periods and apparent brightnesses. Calculate their distances. The Hubble Space Telescope has been crucial for this. HST can resolve individual Cepheids in galaxies out to about 130 million light-years away. That's far beyond the reach of ground-based telescopes, which struggle to separate individual stars in distant galaxies due to atmospheric blurring. From space, HST gets sharp images that can pick out individual stars, even in crowded galaxy environments. Adam Rees and his team have used HST to observe Cepheids in 42 galaxies. Each observation requires multiple visits, spread over weeks or months to capture the full pulsation cycle. You need at least a dozen observations of each star to accurately measure its period and average brightness. For a galaxy containing hundreds of observable Cepheids, that's thousands of individual measurements. The data reduction and analysis are painstaking. You have to identify which stars are Cepheids, distinguish them from other variable stars, measure their periods accurately, correct for dust extinction, and account for crowding, where multiple stars blend together in the image. All of this takes time and careful work, but the result is a set of galaxy distances with typical uncertainties of about 3 to 5%. That's pretty good. The next step is Type 1, a supernovae. These are stellar explosions that reach remarkable peak brightnesses, about 5 billion times more luminous than the Sunday. They're bright enough to be seen across the entire observable universe. A Type 1, a supernova in a galaxy a billion light-years away, can be detected and measured with modern telescopes. This makes them ideal for measuring distances to very remote galaxies. The physics behind Type 1, a supernovae, involves white dwarfs, the dense remnants of stars like the Sun after they've exhausted their nuclear fuel. A white dwarf is supported against gravity by electron degeneracy, pressure, a quantum mechanical effect where electrons resist being compressed beyond a certain density. For a white dwarf to exist stably, it must be below about 1.4 solar masses, known as the Chandrasekhar limit. Above this mass, electron degeneracy pressure can't support the star, and it collapses. In a binary system, a white dwarf can accrete matter from a companion star. As the white dwarf's mass grows, it approaches the Chandrasekhar limit. When it exceeds 1.4 solar masses, or gets very close, the conditions in its core become extreme enough to trigger runaway carbon fusion. Carbon nuclei fuse into heavier elements, releasing enormous energy. The fusion spreads through the white dwarf in seconds, converting a significant fraction of its mass into iron group elements and releasing enough energy to completely unbind the star. The white dwarf explodes, dispersing its material into space at velocities of 10,000 to 20,000 kilometers per second. Because all Type 1, a supernovae, reach approximately the same mass before exploding, they all release similar amounts of energy and reach similar peak luminosities. There's some variation, about 10 to 20% scatter in peak brightness, but much of this can be corrected for. Brighter supernovae take longer to fade. Dimmer ones fade more quickly. This relationship, called the width-luminosity relation, allows you to standardize the peak brightness, measure how quickly the supernova fades after maximum light, apply a correction, and you can predict its true peak luminosity with an uncertainty of only about 7%. Now, you can use supernovae as standard candles. Observe a Type 1a in a distant galaxy, measure its apparent peak brightness and its light curve shape, calculate its true luminosity using the width-luminosity relation, and determine the distance. The calibration of supernova absolute brightness comes from observing supernovae in galaxies where the distance is known from Cepheids. This ties the supernova distance scale to the Cepheid distance scale, which in turn ties to parallax. It's all connected. A chain from nearby stars, measured geometrically, to distant galaxies measured using exploding white dwarfs. Each link in the chain must be carefully forged. Any systematic error in one link propagates to all subsequent links. If Cepheid distances are wrong by 5%, supernova distances will be wrong by 5%, and the inferred Hubble constant will be wrong by 5%. This is why calibration is so critical. Now let's talk about the cosmic microwave background approach. This is fundamentally different. You're not building up distances step by step. Instead, you're using a snapshot of the entire universe when it was very young and inferring properties from that snapshot. The cosmic microwave background was emitted when the universe was 380,000 years old. Before this time, the universe was a hot, ionized plasma. Free electrons scattered photons constantly, making the universe opaque like fog. You couldn't see through it. As the universe expanded and cooled, It eventually reached a temperature of about 3000 Kelvin, cool enough for electrons and protons to combine into neutral hydrogen atoms. This is called recombination, though the name is a bit misleading because the electrons and protons weren't combined before, they were separate. Once atoms formed, photons could travel freely. The universe became transparent. The photons that were released at that moment have been traveling through space ever since, stretched by cosmic expansion from visible light to microwave wavelengths. Today, those photons form a nearly uniform glow across the entire sky with a temperature of 2.725 Kelvin. But superimposed on this uniform glow are tiny fluctuations, variations of about 1 part in 100,000. These fluctuations are the imprints of sound waves that propagated through the plasma before recombination. Here's how it works. In the very early universe, quantum fluctuations during an epoch called inflation were stretched to macroscopic scales. These fluctuations created regions of slightly higher and slightly lower density. Higher density regions had stronger gravity, pulling in more matter, but the plasma was hot and had pressure which resisted the compression. This set up sound waves, oscillations where regions alternately compressed and expanded. Different wavelengths of sound waves behaved differently. Some wavelengths had time to oscillate once or multiple times before recombination. Others were caught mid-oscillation. The oscillations left an imprint in the distribution of matter at recombination, which shows up as temperature variations in the CMB. Hot spots correspond to regions that were compressed, cool spots to regions that were rarefied. By measuring the pattern of hot and cool spots across the sky, cosmologists can determine the wavelengths of the sound waves and how many times they oscillated. The wavelengths are related to fundamental physics. The speed of sound in the early universe plasma depends on the ratio of radiation to matter. More matter means higher inertia, slower sound speed, shorter wavelengths. The number of oscillations depends on how long the universe took to cool, from the end of inflation to recombination. This depends on the expansion rate, which depends on the universe's total energy density. More energy means faster expansion, less time for oscillations. All of this is encoded in the CMB temperature fluctuations. The statistical pattern of hot and cool spots is usually characterized by something called the power spectrum. This is a graph showing how much fluctuation power exists at different angular scales. Large angular scales correspond to long wavelength sound waves. Small angular scales correspond to short wavelength sound waves. The power spectrum has a series of peaks. The first peak corresponds to sound waves that were maximally compressed at recombination. The second peak corresponds to sound waves that had completed one full oscillation and were maximally rarefied. The third peak corresponds to waves that were maximally compressed on their second oscillation, and so on. The positions, heights, and shapes of these peaks depend on cosmological parameters, including the Hubble constant, the matter density, the dark energy density, the baryon density, and others. By fitting a theoretical model to the observed power spectrum, you can extract values for all these parameters. The Planck satellite measured the power spectrum with exquisite precision. Its data extends to very small angular scales, capturing dozens of peaks. The fit to the data is extraordinarily good. The lambda CDM model with 6 free parameters matches the observed power spectrum almost perfectly. The residuals, the differences between model and data, are tiny, consistent with measurement noise. This is a triumph of modern cosmology. A theoretical model based on general relativity and well-understood physics accurately predicts the detailed pattern of temperature fluctuations in a snapshot of the infant universe. From this fit, Planck inferred a Hubble constant of 67.4 kilometers per second per megaparsec, with an uncertainty of less than 1%. This uncertainty is purely statistical, based on the noise in the measurements and how well the model constrains the parameters. It doesn't include possible systematic errors in the theoretical model itself, and this is where concerns arise. Lambda CDM assumes certain things. It assumes general relativity is correct. It assumes the universe is homogeneous and isotropic on large scales. It assumes dark matter and dark energy exist and behave in certain ways. It assumes the standard model of particle physics correctly describes the behavior of matter and radiation. If any of these assumptions is wrong, the inferred Hubble constant could be wrong. There's been extensive effort to test these assumptions. General relativity has passed every experimental test so far. Observations of large-scale structure confirm the universe is very close to homogeneous and isotropic on the largest scales. Dark matter's existence is supported by multiple independent lines of evidence, from galaxy rotation curves, gravitational lensing, the CMB, and structure formation. Dark energy's existence is supported by supernova observations, the CMB, and measurements of the universe's large-scale geometry. The standard model of particle physics has been tested to incredible precision in particle accelerators and correctly predicts the behavior of all known particles. So all the assumptions seem solid. But maybe there's something subtle we're missing. Maybe there's a small deviation from general relativity that only manifests at cosmic scales. Maybe dark energy isn't perfectly constant, but evolves slowly over time. Maybe there's an additional light particle species that contributes to the radiation density in the early universe. Any of these could affect the CMB in ways that alter the inferred Hubble constant. One specific proposal involves something called early dark energy. The idea is that in addition to the dark energy that dominates today, there was an additional component of dark energy in the early universe that has since decayed away. This early dark energy would have contributed to the expansion rate when the CMB was formed, making the universe expand faster than lambda CDM predicts. If the universe was expanding faster, the time from inflation to recombination was shorter. Sound waves had less time to oscillate. The peaks in the CMB power spectrum shift. When you fit lambda CDM to data that actually includes early dark energy, you infer a higher Hubble constant to compensate for the shifted peaks. With early dark energy included, models can match both the Planck CMB data and the distance ladder measurements simultaneously. The Hubble constant comes out to around 71 kilometers per second per megaparsec, nicely splitting the difference. The problem is that early dark energy is an ad hoc addition. There's no independent evidence for it. No particle physics theory predicts it. It's introduced specifically to resolve the Hubble tension. Scientists are wary of such additions because they feel contrived. You're adding new physics without clear motivation beyond fixing a problem. That said, if multiple independent lines of evidence eventually point toward early dark energy, it might be accepted. The same thing happened with dark energy itself. When supernova observations in 1998 suggested the universe's expansion was accelerating, many scientists were skeptical. The data was limited, and the implications were profound. But as more supernovae were observed, as the CMB was analyzed, as large-scale structure surveys were conducted, all the evidence converged on dark energy. Now, it's a standard part of cosmology. Maybe early dark energy will follow a similar path. Another possibility involves extra radiation in the early universe. The standard model includes 3 species of neutrinos. These are nearly massless particles that interact very weakly with matter. In the early universe, when temperatures were very high, neutrinos were in thermal equilibrium with photons and other particles. They contributed to the radiation density and affected the expansion rate. As the universe cooled, neutrinos decoupled and free-streamed through space. Their energy density diluted as the universe expanded, but they remained relativistic for a long time. The CMB is sensitive to the neutrino density through its effect on the expansion rate and on the growth of structure. If there were additional neutrino species or other light particles that behaved similarly, the radiation density in the early universe would be higher. This would speed up the expansion, similar to early dark energy, and shift the CMB power spectrum peaks. Fitting lambda CDM to the data without accounting for the extra radiation would lead to an incorrect Hubble constant. Models with extra radiation can also reconcile the Planck and distance ladder measurements. The catch is that particle physics gives us no reason to expect extra neutrino species. The standard model includes exactly 3 neutrinos, and this has been confirmed by measurements at particle colliders. The decay width of the Z boson, a fundamental particle, depends on how many neutrino species exist. Measurements show the Z boson decays in ways consistent with exactly 3 light neutrinos, so adding extra neutrino species requires going beyond the standard model. Not impossible, but it requires new physics. Maybe the extra radiation isn't neutrinos. Maybe it's axions, hypothetical particles predicted by some theories but never detected. Maybe it's some other exotic particle. Again, there's no independent evidence, so scientists are cautious. There's also been discussion about modifying gravity itself. General relativity is a classical theory, meaning it doesn't include quantum mechanics. At very small scales, in extreme gravitational fields like near black hole singularities or in the early moments of the Big Bang, quantum effects should become important. We need a theory of quantum gravity to fully describe these regimes. String theory and loop quantum gravity are 2 approaches to quantizing gravity, but neither has made testable predictions yet. Maybe quantum corrections to general relativity become important at cosmic scales in subtle ways. Maybe the relationship between matter, energy, and space-time curvature isn't exactly what Einstein predicted when you account for quantum effects. Such modifications could affect cosmic expansion and alter the CMB in ways that change the inferred Hubble constant. But no specific quantum gravity theory has made predictions detailed enough to test against the Hubble tension. It's speculative at this point. Modified Newtonian dynamics, or MOND, is another alternative to general relativity that's been proposed primarily to explain galaxy rotation curves without dark matter. MOND modifies the law of gravity at very low accelerations. It's been somewhat successful at matching galaxy observations, but it fails to explain other phenomena like gravitational lensing and the CMB, and it doesn't naturally address the Hubble tension. So most cosmologists don't see MOND as a viable solution. What all of this tells us is that resolving the Hubble tension isn't straightforward. There's no obvious fix, no simple systematic error that accounts for the discrepancy. Both measurements have been scrutinized extensively. Multiple independent teams have analyzed the data. Different methods for cleaning foregrounds, correcting for systematics, and modeling the physics have been tried. The tension persists. This suggests something deeper is going on. Either there's a subtle effect we haven't thought of yet, or our cosmological model is missing a piece. The exciting thing is that we'll figure it out eventually. New data keeps coming in. JWST is observing more Cepheids and more distant objects with unprecedented clarity. Its near-infrared and mid-infrared cameras can see through dust better than Hubble, reducing one source of systematic uncertainty. Early JWST observations of Cepheids have confirmed the distance ladder results, showing that dust extinction isn't the culprit behind the Hubble tension. Future CMB experiments like the Simons Observatory and CMB Stage 4 will map the microwave sky with even higher sensitivity and resolution. They'll probe smaller angular scales and detect polarization patterns with exquisite precision. This will tighten constraints on cosmological parameters and might reveal subtle features in the CMB that point toward new physics. Gravitational wave observations from LIGO, Virgo, and future detectors like CAGRA and LIGO India will provide more distance measurements through binary mergers. As the number of detected mergers grows, the statistical uncertainty in the gravitational wave Hubble constant measurement will shrink. Within a decade, gravitational waves might provide a decisive measurement that clearly favors one side of the tension or reveals something entirely unexpected. Strong gravitational lensing studies are also expanding. Large sky surveys are discovering more quasar-galaxy lens systems. With more lenses comes better statistics and tighter constraints. The H0 LICO collaboration and similar efforts are pushing to measure the Hubble constant from lensing with a few % precision. This could break the deadlock if the lensing measurement clearly agrees with one of the other methods. All of these approaches are converging. In a few years, we'll have multiple independent measurements of the Hubble constant, each with uncertainties of a few % or better. If they all agree, we'll know the answer. If they continue to disagree, we'll know for certain that something fundamental is wrong with our cosmological model. Either way, we'll have learned something profound. The history of science is full of examples where unexpected observations led to revolutionary discoveries. The orbit of Mercury didn't quite match Newtonian predictions. The discrepancy was tiny, only 43 arcseconds per century, but it was real. Einstein's general relativity explained it perfectly, showing that space and time are curved by mass and energy. Blackbody radiation didn't follow classical predictions. Objects heated to high temperatures emitted radiation with a spectrum that classical physics couldn't explain. Max Planck resolved the problem by proposing that energy is quantized, coming in discrete packets. This was the birth of quantum mechanics. The speed of light appeared to be the same for all observers, regardless of their motion. This contradicted Galilean relativity, where velocities simply add. Einstein resolved the contradiction with special relativity, showing that space and time are relative and interconnected. In each case, a small discrepancy between theory and observation led to a complete rethinking of fundamental physics. The Hubble tension might be similar. We have two measurements that should agree but don't. The discrepancy is only about 8 or 9%, but it's statistically significant and persistent. Maybe it's pointing toward a revolution in how we understand the cosmos. Or maybe it's a stubborn systematic error that will eventually be identified and corrected. We won't know until we gather more data and test more ideas. That's the essence of science. You make observations, develop theories to explain them, test those theories against new observations, and refine your understanding. It's an iterative process, slowly converging on truth. Sometimes the path is smooth and steady. Sometimes you hit roadblocks and have to rethink your assumptions. The Hubble tension is one of those roadblocks, but it's also an opportunity. An opportunity to test our theories more rigorously, to develop new measurement techniques, and potentially to discover new physics. That's why cosmologists are so energized by this problem. It's challenging, yes. But challenges are where progress happens. When everything agrees perfectly, when all the measurements match predictions, there's less to learn. You're confirming what you already know. But when measurements disagree, when observations don't fit the model, that's when you're forced to dig deeper and think harder. That's when new discoveries are made. The Hubble tension is a gift in that sense. It's telling us there's something we don't understand, something important, and figuring out what that something is will advance our knowledge of the universe. So while it's frustrating for cosmologists who would prefer their measurements to agree, it's also exciting. The next decade will be crucial. New telescopes, new detectors, new techniques, more Cepheids, more supernovae, more CMB maps, more gravitational waves, more lensing systems. The data will keep improving, the precision will keep increasing, and eventually the truth will emerge. We'll solve the Hubble tension. We'll know why the measurements disagreed. We'll understand whether our cosmological model needs revision or whether we were just making a subtle mistake all along. And we'll know the true expansion rate of the universe. 67 kilometers per second per megaparsec. 73 kilometers per second per megaparsec. Or something entirely different. Whatever the answer, it will be definitive. And it will mark another milestone in humanity's quest to understand the cosmos. That quest has been ongoing for thousands of years. Ancient astronomers tracked the motions of planets and stars, trying to make sense of the heavens. They developed models, epicycles, and deferents to predict celestial motions. Copernicus revolutionized astronomy by placing the sun at the center of the solar system. Kepler discovered that planets move in ellipses, not circles, and found mathematical laws governing their motion. Galileo used the newly invented telescope to observe the moons of Jupiter, the phases of Venus, and the mountains on the moon. Newton developed universal gravitation and laws of motion that explained why planets move as they do. These discoveries laid the foundation for modern astronomy. In the 20th century, the pace accelerated. Hubble discovered cosmic expansion. Zwicky and Rubin discovered dark matter. Penzias and Wilson discovered the cosmic microwave background. Perlmutter, Schmidt, and Rees discovered dark energy. Each discovery expanded our view of the universe and raised new questions. Now, in the 21st century, we're grappling with the Hubble tension and other mysteries. What is dark matter? What is dark energy? What happened in the first moments after the Big Bang? Are there other universes beyond our own? Is our physics complete, or are there fundamental forces and particles we haven't discovered yet? These are deep questions, perhaps the deepest questions science can ask. And we're making progress. We might not have all the answers yet, but we're getting closer. The Hubble tension is part of that progress. It's a signpost pointing towards something we don't yet understand. Follow the signpost, do the work, gather the data, and we'll find the answer. That's what makes cosmology so compelling. It's humanity's attempt to understand the universe we inhabit, to know where we came from and where we're going. It's an intellectual endeavor of the highest order, requiring sophisticated mathematics, cutting-edge technology, and creative thinking. But it's also fundamentally human. We look up at the stars and we wonder. We've always wondered. What are those lights in the sky? How far away are they? What are they made of? How did they get there? How did we get here? These questions are as old as humanity itself. What's changed is that we now have tools to answer them. We have telescopes that can see across billions of light years. We have satellites that can measure photons from the Big Bang. We have mathematical theories that predict the behavior of space and time. We have computers that can simulate the evolution of the entire universe. And we have dedicated scientists who spend their careers pursuing these questions, driven by curiosity and a desire to understand. The Hubble tension is their current challenge. It's a puzzle that needs solving, and solve it they will, through persistence, ingenuity, and collaboration. That's the scientific community at its best. People from around the world, working together, sharing data and ideas, building on each other's work. No single person will resolve the Hubble tension. It will take many people, many observations, many analyses, many discussions and debates. But collectively, we'll figure it out. We'll understand why the measurements disagreed and what it tells us about the universe. And then we'll move on to the next mystery, the next puzzle, because there will always be another mystery. The universe is vast and complex, and we've only scratched the surface of understanding it. Every answer raises new questions. Every solved problem reveals new puzzles. That's the beauty of science. It's never finished. There's always more to discover, more to learn, more to understand, and that's what makes it worth doing. The Hubble tension is just one chapter in the ongoing story of cosmology. A chapter where measurements don't quite agree, where theories are being tested, where new ideas are being explored. It's an uncertain time, which can be uncomfortable, but it's also an exciting time. We're on the verge of learning something new about the universe. We don't know what it is yet, but we'll find out. And when we do, we'll look back on this period and see it as a turning point. The moment when we realized our cosmological model needed revision, or the moment when we finally tracked down that elusive systematic error. Either way, it will be remembered. So that's the story of the Hubble tension. Two measurements that should agree but don't. A discrepancy that's small but significant, an unsolved problem that's driving new observations and new ideas. And a reminder that science is a process, not a destination. We're always learning, always refining, always discovering. The universe keeps surprising us, and we keep trying to understand it. That's what we do. That's who we are. Curious beings on a small planet, looking out at the cosmos and trying to make sense of what we see. We've come far in our understanding. We know the universe is expanding. We know it had a beginning. We know it's filled with mysterious dark matter and dark energy. We know its age, its composition, its structure. But we don't know everything. We don't know exactly how fast it's expanding. And that's okay. That's what makes the journey worthwhile. The pursuit of knowledge, the quest for understanding, it's what makes us human. And it's what will keep us looking up at the stars, wondering, questioning, and discovering for as long as we exist. Before we close tonight, let's consider what the resolution of the Hubble tension might look like and what it could mean for the future of cosmology. There are really only a few possible outcomes. First, we might discover that the distance ladder measurements have a systematic error we haven't identified yet. Perhaps there's something about Cepheid variables we don't fully understand. Maybe their brightness is affected by their chemical composition in ways that are more significant than we thought. Different galaxies have different metallicities, different abundances of elements heavier than hydrogen and helium. Stars in metal-rich galaxies might behave slightly differently from stars in metal-poor galaxies. If Cepheids in metal-rich environments are systematically dimmer or brighter than our calibration assumes, and if the galaxies we use to calibrate supernovae have different metallicities than our local calibrating galaxies, we could be introducing a systematic bias. Studies have looked at this, comparing Cepheids in different environments, and the effects seem small. But maybe there's a subtle correlation we've missed. Or perhaps there's something about Type 1, a supernovae. We know these explosions aren't perfectly uniform. There are subtypes, spectroscopic variations, differences in how quickly they brighten and fade. We have corrections for some of this variation, the width-luminosity relation being the most important. But maybe the corrections aren't perfect. Maybe there's a population of supernovae that's systematically brighter or dimmer than we think. And maybe this population is more common at certain distances or in certain types of galaxies. If we're systematically including too many of these outlier supernovae in our distance samples, we could be biasing our distance measurements. This seems unlikely because supernova cosmology has been refined over decades. Multiple teams have studied thousands of supernovae. The corrections and calibrations are well tested, but it's possible there's something subtle we've overlooked. Dust extinction is another potential culprit. Dust between us and distant stars absorbs and scatters light, making objects appear dimmer and therefore more distant than they really are. We correct for dust using multiple techniques. We observe at different wavelengths and use the fact that dust extinction is stronger at shorter wavelengths. Blue light is absorbed more than red light, so dusty objects appear redder than they should. By measuring the color and comparing to what we expect, we can estimate how much dust is present and correct the brightness accordingly. But dust properties vary. Not all dust grains have the same size distribution or composition. Dust in some galaxies might extinguish light differently than dust in the Milky Way, which is where most of our calibration comes from. If distant galaxies have systematically different dust properties, our corrections might be wrong. JWST's infrared observations should help with this. Infrared light is much less affected by dust than visible light. By observing Cepheids and supernovae in infrared, we can measure distances with much less uncertainty from dust. So far, JWST results have confirmed the distance ladder measurements, suggesting dust isn't the problem. But there's still more data to analyze. The second possible outcome is that the CMB measurements have a problem. This seems even less likely because the CMB analysis is based on well-understood physics and has been cross-checked extensively. But maybe there's foreground contamination we haven't fully removed. Emission from our own galaxy, dust and gas in the Milky Way, produces microwave radiation that can contaminate the CMB signal. Planck observed at multiple frequencies specifically to identify and remove this foreground emission. Different types of foreground emission have different spectral properties, so by observing at many frequencies, you can separate the CMB from the foregrounds. This process, called component separation, has been done carefully with multiple independent methods, all giving consistent results. But maybe there's a subtle foreground component we haven't accounted for. Something faint that has a spectrum similar to the CMB and therefore doesn't stand out in multi-frequency observations. This seems very unlikely, but it can't be ruled out completely. Another possibility is that there are unaccounted for systematics in the satellite instruments, calibration errors, pointing uncertainties, beam asymmetries. All of these can affect the measurements. Planck had a large team of experts who characterized the instruments exhaustively. They published detailed papers describing every aspect of the data analysis and how systematic effects were handled. The level of scrutiny is extraordinary. But instruments are complex, and there's always a possibility of subtle effects that escape detection. If there's an instrumental systematic that affects the large angle measurements more than the small angle measurements, or vice versa, it could shift the inferred cosmological parameters. Again, this seems unlikely given how carefully the data has been analyzed, but it's not impossible. The third and most exciting possibility is that both measurements are correct and our cosmological model is incomplete. This would mean there's new physics we haven't discovered yet. Early dark energy is one proposal, as we discussed. Extra radiation is another. There are other ideas too. Maybe dark matter isn't purely cold. Cold dark matter means the particles are moving slowly, non-relativistically. But maybe some fraction of dark matter is warm, moving at speeds comparable to a significant fraction of light speed. Warm dark matter would behave differently during structure formation, affecting how galaxies and clusters grow. This could leave an imprint in the CMB and in large-scale structure that we interpret as a different Hubble constant. Or maybe there are interactions between dark matter and dark energy. In standard lambda CDM, dark matter and dark energy don't interact. They coexist, but don't directly affect each other. But what if they do interact? What if dark energy's density depends on the dark matter density, or vice versa? This could change how the universe's expansion rate evolves over time, creating a discrepancy between early universe measurements from the CMB and late universe measurements from the distance ladder. Models with interacting dark sectors have been proposed and studied. They can sometimes ease the Hubble tension, but they require fine-tuning parameters to make the interactions work out right. There's no strong theoretical motivation for such interactions, so they're viewed skeptically. But if evidence keeps pointing that direction, they might gain acceptance. Another exotic possibility involves the cosmological principle itself. This is the assumption that the universe is homogeneous and isotropic on large scales, the same everywhere and in all directions. Observations strongly support this. The CMB looks nearly identical in all directions. Large galaxy surveys show that on scales above a few 100 million light-years, the universe looks uniform. But maybe it's not perfectly uniform. Maybe we live in a region that's slightly different from the cosmic average. If we're in a region where the expansion rate is locally faster or slower than the global average, the distance ladder would measure the local rate, while the CMB measures the global rate. This is the local void scenario we mentioned earlier. If we're near the center of a large underdense region, gravity would be weaker here, and the expansion rate could be locally enhanced. The problem is that observations don't support a large local void. Studies of galaxy distributions show that our local environment is fairly typical. There are voids and overdense regions, but no huge void centered on us. To explain the Hubble tension, the void would need to be several 100 million light-years across, with a density deficit of 10 to 20%. That would show up clearly in galaxy surveys. We don't see it. So the local void explanation seems ruled out, unless the void has unusual properties that make it harder to detect. Maybe it's a void in dark matter rather than ordinary matter. Dark matter is much harder to map directly. We infer its presence from gravitational effects. If there were a large dark matter void, it might not show up as obviously in galaxy surveys, but it would still affect galaxy motions and gravitational lensing. Studies of these effects should reveal any large-scale dark matter structures. Again, no strong evidence for a local dark matter void has been found. Perhaps the most radical possibility is that general relativity breaks down at cosmological scales. We've tested general relativity extensively in the solar system, from GPS satellites to planetary orbits to gravitational waves from binary mergers. It works perfectly in all these regimes. But cosmology probes entirely different scales, billions of light-years, and entirely different conditions, the expansion of space itself. Maybe at these scales, quantum effects become important in unexpected ways. Maybe the relationship between matter density and space-time curvature is slightly different than Einstein's equations predict. This wouldn't require throwing out general relativity entirely, just modifying it at the edges, in regimes we haven't fully tested yet. Several modified gravity theories have been proposed over the years. Most are ruled out by observations. They predict things that we don't see, or they fail to match phenomena that general relativity explains perfectly. But the space of possible modifications is enormous. Maybe there's a modification that keeps all of general relativity's successes while resolving the Hubble tension. Finding such a modification is a tall order. It has to match not just the Hubble tension, but everything else we observe: gravitational waves, solar system tests, galactic dynamics, cosmological structure formation, all of it. That's a lot of constraints. Most modified gravity theories fail at least one of these tests. But maybe there's a theory out there we haven't thought of yet. That's the exciting possibility. New physics often comes from unexpected directions. Before general relativity, nobody predicted that space and time would be curved by mass and energy. It was a radical new idea that emerged from Einstein's struggle to make gravity compatible with special relativity. Before quantum mechanics, nobody predicted that energy would come in discrete packets or that particles would have wave-like properties. These ideas emerged from attempts to explain specific experimental results that classical physics couldn't handle. The Hubble tension might be similar. A small discrepancy that seems like a technical problem, but actually points toward a deeper truth about nature. We won't know until we solve it, and solving it will require continued effort from many people using many different approaches. JWST will keep observing Cepheids and supernovae, improving distance measurements. Future CMB experiments will map the microwave sky with higher fidelity, checking Planck's results and extending them to smaller angular scales. Gravitational wave detectors will observe more binary mergers, building up an independent sample of distance measurements. Lensing surveys will find more quasar-galaxy lenses, improving the time-delay cosmography measurements. Baryon acoustic oscillations, another distance measurement technique we haven't discussed in detail, will be measured in upcoming large-scale structure surveys. This technique uses sound waves in the early universe, similar to the CMB, but looks at how matter distributed itself rather than radiation. The sound waves left an imprint in the distribution of galaxies, a characteristic scale called the baryon acoustic oscillation scale. By measuring this scale at different distances and comparing to the expected size based on CMB observations, we can infer how the universe has expanded. This provides another completely independent measurement of cosmological parameters, including the Hubble constant. Current baryon acoustic oscillation measurements tend to favor the lower Hubble constant values from the CMB, but the uncertainties are still fairly large. Future surveys, like the Dark Energy Spectroscopic Instrument, DESI, and the European Space Agency's Euclid mission, will measure baryon acoustic oscillations with much higher precision. Within a few years, we'll have very tight constraints from this method. If baryon acoustic oscillations agree with the CMB, that strengthens the case that the CMB measurement is correct and something is wrong with the distance ladder. If they agree with the distance ladder, that's evidence the CMB interpretation might be wrong. If they fall in between, or disagree with both, that points towards something even more interesting, perhaps a genuine evolution in the expansion rate that our models don't capture. All of this data will converge over the next decade. We'll have multiple independent measurements, each with a few % uncertainty, all testing the same fundamental question. What is the universe's expansion rate? With enough data, patterns will emerge. Maybe we'll find that all the late-time measurements, distance ladder, gravitational waves, lensing, baryon acoustic oscillations, all agree on a higher Hubble constant, around 73. And the early time measurements, CMB and maybe primordial nucleosynthesis constraints, agree on a lower value around 67. That would strongly suggest the expansion rate has evolved in ways our models don't predict. It would point toward new physics in the dark sector, either dark matter or dark energy, behaving unexpectedly. Or maybe we'll find that one specific technique has been wrong all along. Perhaps future JWST observations will reveal a systematic error in Cepheid distances that nobody caught before. Perhaps future CMB experiments will find foreground contamination that Planck missed. Perhaps gravitational wave measurements will clearly favor one side over the other. Any of these would resolve the tension, though the resolution would be less exciting than discovering new physics. But even finding and fixing a systematic error is valuable. It teaches us to be more careful, to check our assumptions more thoroughly. It improves the rigor of our methods, and it ultimately gives us more reliable results. The history of astronomy is full of systematic errors that were eventually identified and corrected. Hubble's original measurement of the Hubble constant was off by a factor of 7 because he didn't know about different types of Cepheids. That error was corrected in the 1950s. Early measurements of the solar neutrino flux were off because we didn't understand neutrino oscillations, the fact that neutrinos can change flavor as they travel. That was resolved in the early 2000s. Measurements of the cosmic microwave background temperature were uncertain by factors of 2 until satellite observations in the 1990s. Now we know it to a precision of better than 0.01%. Science corrects itself. Errors are identified, methods are improved, measurements converge on the truth. It takes time, sometimes decades, But eventually we get there. The Hubble tension will be resolved. Maybe quickly, within 5 years. Maybe slowly, taking a decade or more. But it will be resolved. And when it is, we'll look back on this era as a critical period in cosmology. A time when our measurements were good enough to reveal a discrepancy, but not yet precise enough to explain it. A time of uncertainty and debate, of competing hypotheses and intensive observation campaigns. A time when cosmology was vibrant and dynamic, grappling with fundamental questions about the universe. That's where we are now, in the midst of the tension, working toward resolution. It's an exciting place to be. For the scientists involved, it's the frontier of knowledge. For the rest of us, it's a window into how science works, how discoveries are made, how theories are tested, how knowledge advances. The Hubble tension isn't just about one number, the expansion rate of the universe. It's about the process of understanding reality through observation, experimentation, and reason. It's about following evidence wherever it leads, even when it leads to places we didn't expect. It's about being humble enough to admit when we don't know something and persistent enough to keep searching for answers. These are the virtues of science, and they're on full display in the effort to resolve the Hubble tension. So as we conclude tonight, remember this: the universe is expanding. We've known that for nearly a century. But exactly how fast it's expanding remains uncertain. Two of our best methods disagree by about 8 or 9%. That might not sound like much, but it's enough to keep cosmologists awake at night. It's enough to drive new observations and new theoretical work. It's enough to potentially reveal new physics and reshape our understanding of the cosmos. Over the next decade, we'll gather more data, test more hypotheses, and inch closer to the truth. Maybe we'll discover new particles or new forces. Maybe we'll find that dark energy evolves over time. Maybe we'll uncover subtle errors in our measurements. Or maybe we'll find something completely unexpected, something we can't even imagine yet. That's the nature of exploration. You don't always know what you'll find. But you keep looking because the search itself is worthwhile. The universe has been revealing its secrets to us slowly, one discovery at a time. The expanding universe, dark matter, dark energy, the cosmic microwave background, gravitational waves. Each discovery has transformed our understanding and raised new questions. The Hubble tension is the latest chapter in this ongoing story, and like previous chapters, it will eventually lead to resolution and new understanding. We'll solve this puzzle. We'll figure out why our measurements disagreed and what it tells us about the universe. And then we'll move forward, asking deeper questions, making new observations, and continuing the eternal human quest to understand the cosmos. Because that's what we do. We're explorers, investigators, seekers of truth. We look up at the vast universe and we don't just wonder, we work to understand. We build telescopes and satellites, we develop mathematical theories, we make careful measurements and thoughtful analyses. We collaborate across borders and disciplines, sharing knowledge and building on each other's work. And slowly, incrementally, we expand the sphere of human knowledge. The Hubble tension is one small piece of that larger endeavor. But it's an important piece because it touches on fundamental questions about the nature of reality. How fast is the universe expanding? What is it made of? How did it begin? Where is it headed? These questions have been asked for millennia. Now, for the first time in human history, we have the tools to answer them rigorously. Not with mythology or speculation, but with observation and mathematics. That's extraordinary. And the fact that we still have mysteries to solve, that we still encounter observations that don't quite fit our models, that's what keeps it exciting. Science isn't about knowing everything. It's about the journey of discovery. The Hubble tension is part of that journey, and we're fortunate to be here, witnessing it unfold. So when you look up at the night sky, think about this. Every photon of starlight that reaches your eye has been traveling through expanding space. The universe those photons traversed is bigger now than when they started their journey. And the rate of that expansion, the Hubble constant, is something we're still figuring out. It's humbling to realize how much we still don't know, but it's also inspiring to see how far we've come and how much we're continuing to learn. The universe is vast, ancient, and full of wonders, and we're here, on this small planet, working to understand it all. That's the story of the Hubble tension. That's the story of cosmology. And that's the story of humanity's endless curiosity about the cosmos.